So hi everyone, welcome to this session. So as I said earlier, whether you are remote or in Vienna, you can ask questions. Please, it will be easier if you do so by writing them in the chat in Zoom. It will be easier for me. Well, if you're in Vienna, you may also ask them directly, but I'm not sure that everyone will, in this case, hear them. So please prefer the chat if possible. And then, we'll start with our first author. So he's not in Vienna, so we will have a video and then the questions. The authors are Anthony Karahalios and Willem-Jan van Hoeve, and they are going to present us variable ordering for decision diagrams.
Hi, my name is Anthony Karahalios, and today I will be presenting on using portfolios of variable orderings when working with decision diagrams. This is joint work with Professor Willem-Jan van Hoeve, and we are from Carnegie Mellon University. A decision diagram is often used to represent a set of solutions to a combinatorial optimization problem. Today, we will use the graph coloring problem as an example of such a problem. The graph coloring problem is defined as given a graph of vertices and edges, use the minimum number of colors such that each vertex is assigned a color and no two adjacent vertices have the same color. On the bottom right, we have an example of a solution for this graph, and there are many applications to this problem such as scheduling and rostering. We'll talk about two different approaches to solving this problem today. First, let's discuss a MIP formulation by Mirotra and Truchet that is currently used in the state-of-the-art code to solve this problem. We'll define a color class as a subset of non-adjacent vertices in the graph. And in the formulation, we're going to use binary variables xs that will equal 1 if a color class is selected in the coloring and 0 otherwise. So if we let script s be the set of all possible color classes for our graph, the formulation looks like this, where we're minimizing the number of color classes necessary to such that each vertex is in exactly one color class. For our example graph, you can see a solution here where x14 and x23 are the two color classes that are chosen, while these color classes are not chosen in the solution. Because there may be an exponential number of possible color classes in the graph, column generation is used, and because we're dealing with binary variables, there's a branch and price heuristic as well. Now we'll discuss the second approach, a decision diagram approach that is going to be used for the rest of the presentation when we're discussing our variable orderings and our variable ordering portfolios. So given a graph, an exact decision diagram is an auxiliary graph that encodes exactly all of the possible color classes as RT paths in the auxiliary graph. For example, this RT path would represent the color class 1, 2, where the solid arcs are indicating which vertices are chosen in our color class. So using this exact decision diagram, we could create a MIP that uses integer variables YA that represent the flow through an arc, and our MIP formulation would minimize the number of paths or colors necessary such that each vertex receives a color or is on one path, and we have conservation of flow and integral constraints. If we solve this MIP formulation on our exact decision diagram, we will get the solution to the graph coloring problem, or a solution. Here we have two paths, a blue color class with vertices 1 and 4, and a green color class with vertices 2 and 3. Now, we'll have a similar problem to the Mirotra-Truchet MIP formulation where the exact decision diagram can be exponentially large, and this would mean that our MIP would be very difficult or impossible, very difficult to solve. So in 2020, von Hoeve came up with an algorithm to deal with this problem in a similar way to how column generation works on the other formulation. The algorithm starts with a with-one relaxed decision diagram that encodes all of the feasible color classes, but also infeasible ones. So if we solve the MIP formulation from the previous slide on this graph, we will get a solution of one color class, 1, 1, 1, 1, 1, that is clearly infeasible. So we would look for a conflicting edge, like 1, 3 should not have the same color, and we would refine the diagram to ensure that 1, 1, 1, 1, 1 is no longer a solution or an RT path in our graph. We continue to solve the MIP and look for conflicts and refine the diagram at each iteration until we find a solution that has no conflicts and is optimal. You'll see that we're getting lower bounds on the number of colors necessary to color the graph at each iteration because we're using a relaxed decision diagram. So in this algorithm by von Hoeve, we have some decisions to make on what we want to do at each iteration. First, we need to decide what order our variables what ordering we use for the variables in our decision diagram. Also, at each iteration, we're solving this MIP formulation. Do we want to solve the MIP or solve an LP relaxation and work with that solution? At each iteration, we might have multiple color classes. Do we want to look for the first conflict that we find in a color class and resolve that and move on? Or do we want to resolve all the conflicts that we see in all the color classes and then iterate from there? And also, which upper bound heuristic would we like to use as well? Now, von Hoeve found that of 137 Dimax instances, which is a common benchmark set of instances for the graph coloring problem, with a timeout of 1 hour on the algorithm, 54 of the instances were solved to optimality using a variety of these settings. We're going to discuss the variable ordering today, as it's been shown in previous literature that this is one of the most important decisions to make when working with decision diagram-based algorithms. So why work on the variable ordering? Well, the variable ordering affects the size of the exact decision diagram. Given a path graph, we can see that if we order the variables 1, 2, 3, 4, 5, the exact decision diagram would be this one of about 10 nodes. But if we use an ordering 4, 3, 1, 2, 5, the exact decision diagram becomes much larger. Now, the size of the exact decision diagram is going to affect the performance of our iterative refinement algorithm. We show this via an experiment that we ran, similar to one that was run by Bergman et al. That showed a similar result, where we chose 300 different variable orderings. We randomly generated these variable orderings, and on a single graph instance, we used Jean, which is a graph instance in the Dimax set. We found the size of the exact decision diagram using the variable ordering, and then we ran the iterative refinement algorithm on a decision diagram using that ordering and reported the lower bound at the end of 5 minutes. And what we see is that a variable ordering that corresponds to a smaller exact decision diagram also has a larger lower bound or better performance at the end of 5 minutes. Let's discuss variable orderings that we use in our experiments. We use a lexicographic ordering, which orders the vertices as their input by the user. A maximum connectivity / degree ordering, where we order the vertices one at a time, at each iteration choosing the vertex that has the most vertices adjacent to it already in the ordering, using the maximum degree as a tiebreaker. A desatter ordering, which is a commonly used graph coloring heuristic by Bray laws, that colors the vertices one at a time, and at each iteration it chooses the uncolored vertex that has the most colors adjacent to it that have already been colored by the algorithm. A maximal path decomposition and a maximal clique decomposition to try to exploit those structures, and a minimum width ordering by Freuder, where minimum width means we're trying to find the minimum way to order the vertices such that we're minimizing the maximum number of dependencies any vertex has that come before it in the ordering. That's what's meant by with. And we ran the decision diagram based algorithm on all the Dimax instances using each of these variable orderings. And here we graph the frequency that a variable ordering achieves the best lower bound of any of the variable orderings at a few different time points. And what we see is that no single variable ordering performs the best on all 137 Dimax instances. So this leads us to the idea of using a variable ordering portfolio, that instead of just always using a single variable ordering, we can have a portfolio of them that uses an algorithm that decides in a smart way which single ordering or group of orderings should be used in our hour runtime. Let me give you a couple examples of what these portfolios might look like. In this first example, we run the algorithm in rounds of doubling amounts of time, where we start with a uniform portfolio where all the variable orderings are run for an equal amount of time, so 1/6 of a second each. And then maybe as certain variable orderings start to perform better or have better lower bounds, they might receive a larger portion of the runtime. In the second example, we have two phases: an exploration phase where all the variable orderings are run for a fixed amount of time, and an exploitation phase where, given the performance of the algorithms in that first 2 minutes, we might choose a single variable ordering to run for the rest of the runtime. We experimented with 4 different types of variable ordering portfolios: a uniform portfolio that round by round just stays with an equal amount of time for each variable ordering, a predictive portfolio by Meslieu and Schwanger that trains a classification model using some Culberson graphs and some graph characteristics such as number of nodes, number of edges, maybe how many colors the DSAT or heuristic comes up with. And we ran the algorithm using all the variable orderings on the training instances and classified each of these with the best variable ordering that worked for them. And then given a new instance, we predict which single variable ordering we're going to run for the entire time. Next, a low knowledge portfolio at Beck and Freuder, where we're split up in these exploration and exploitation phases, and the variable ordering chosen in the exploitation phase is chosen by one of these 3 criteria: either the maximum lower bound achieved, the maximum slope, or p-slope, which is the maximum mean change in lower bound if we split up the exploration phase into intervals. And then the last criteria is p-extrap, which is the lower bound at the end of the exploration phase, extrapolated by the p-slope value to the end of the hour runtime, choosing the variable ordering that has the highest lower bound in that sort of extrapolated method. Finally, a dynamic online portfolio that starts with the uniform portfolio and runs in these rounds of doubling time, and at each round gives an LP bonus for the new maximum lower bound, or a delta bonus for the maximum change in lower bound, or a tie bonus if none of the variable ordering's lower bounds have changed, that reverts the runtime distribution back to the uniform distribution. So we ran the 4 different types of portfolios on all their different settings for the Dimax instances, and here we choose the best setting for each of the 4 different portfolio strategies, and we choose that to show this graph of how they performed. We also show the performance against some code by Held, which is the state-of-the-art code that uses the Truchet column generation approach. And the Held code solves about 60 Dimax instances optimally. Behind this code, at the end of an hour, behind the Held code is an oracle that uses the decision diagram algorithm and knows the best variable ordering for the instance and uses that one. Behind this is the PCOS low knowledge approach that solves 55 instances optimally, and then the dynamic online approach that solves 54 instances optimally. Right behind this is the uniform portfolio, which is kind of our benchmark. We also ran the experiments on the Culberson instances, which are the ones that we use to train the predictive model. And unsurprisingly, the predictive model, a random forest here, performs as one of the best variable orderings using these Culberson instances, where it didn't perform as well on the Dymax set. So to summarize, the dynamic ordering portfolios perform the best. On the Dymax set, the predictive variable ordering performed better on graphs that were similar to the ones it trained on. And one interesting thing that we found is different variable orderings yield different upper bounds. So a portfolio can outperform the oracle that chooses the single best variable ordering, because a portfolio might use two variable orderings where one achieves the best lower bound and another achieves the best upper bound that can close an instance. Finally, the portfolio approach is generic, can be applied to other decision diagram based problems. So not only the graph coloring problem and not only this algorithm, but many others as well. Thank you for listening, and I would be happy to answer any questions that you may have.
Thank you, Anthony. So now we may have questions. So Anthony, can you read? There is a question by Sharan in the chat. Is asking, how does using a portfolio compare to using 10 copies of the same heuristic, but with different randomizing the tie-breaking seeds?
Hey, that is a great question. We haven't, I guess, experimented with using different tie-breaking seeds. I assume that randomization might help out a little bit, but I think what we were seeing is that we need maybe a different algorithm kind of portfolio, and like an entirely different one, instead of just breaking random seeds, to kind of get more improvements on some of these graphs.
Thank you. So I see a hand, so I assume it means we have a question in Vienna, correct?
Two, actually.
Two, okay. So we have time for two questions.
Okay, I have a question. Because you consider the different ordering, and then you are going to relax the MDD you obtain. So do you have any information about the relation that varies between the starting MDD and the relaxed MDD? I mean that, do you know if, for instance, we can have a larger MDD, but a relaxation that could be better or something like that? Do you have some information?
Can you repeat what you mean by that?
I mean that you compute an MDD and then you are going to relax an MDD. So you try to have a smaller MDD in order to improve the relaxation, if I understand well. So my question is, do you have any insight about the size of the MDD and the quality of the relaxation?
Yeah, that's a great question. I think right off the bat, we're not sure how a variable ordering is going to perform for the MDD. We always start with that with one diagram and start doing the conflict separations at each iteration. There may be some, I guess, metrics that we could take into consideration about a certain ordering on a graph that might help us out. But yeah, I don't think we totally know how the performance is going to go on any instance for a variable ordering.
Actually, I had the same question. So Sharon is also discussing in the chat, but we are running out of time. So maybe we can take the last question from Vienna.
Hello, just a quick question. So you've done the portfolio approach and you see that it works better. Do you have an idea? you get some kind of insight on what's important for these variable orderings based on your portfolio approach. You have like some kind of hint or something like that that can help us maybe design some new kind of heuristics for variable orderings.
Yes, that's a great question. I wish that we had more insights to come up with the best variable orderings. I think what we noticed is that the min width ordering was the one that performed the best for us. And that has to do with the, I guess, number of like how far away vertices, other adjacent vertices, its neighbors are in the graph. So I think that was one of the most important metrics that maybe we can start accounting for as we try to come up with new variable orderings. I think that was the biggest insight for me.
Okay, thank you.
Thank you for the question. So there is a last question in the chat. Do we have 1 minute maybe so that you can answer it? You have it, Anthony?
Yes. Thank you.
So
Did
the
you do any
question is
tests?
whether the benefits come from the specific portfolio you tested or just from trying different orderings?
Yeah, I think what we're going to see is usually you'll need at least a few different variable orderings. I'm not sure how much the size affected it. I think if we only used maybe 3 of the 6 orderings, we might be able to see a similar result because just those 3 might get us to the largest amount of instances. I think if you had too many orderings, it would be a problem. We actually had a couple more in there to start, and because they might be receiving time that could be better spent elsewhere. So that's one insight we had on the size of the portfolio.
But then maybe they should be eliminated quite quickly, right? If they are not efficient.
Yeah, ideally they'd be eliminated right away by if your algorithm's smart enough.
In a perfect world.
Yes.
All right then. Thank you, Anthony. Maybe I'm not sure, but how to do that. Thank you for the nice video.